Now, as we start this webinar, it's only 1 minute past 2 in the UK at the moment, and there will be people joining as we go. Everyone's doing back-to-back meetings at the moment because of the COVID situation, so we like to give people a few minutes to join. But thank you for those who joined on time. The format of these is pretty simple. We'll be running through some slides which are going to be presented and explained to you by Dr. Blair, who's our resident power systems expert. And while he's talking, please realise that obviously that the audience are on mute, but we'd invite you to ask questions of the panelists, and you can do that by using the Q&A button, not the chat button. The chat is disabled in this version of Zoom, but Q&A that allows us to keep an eye on all of the questions that are asked. And while you're asking them, as best as possible, we'll be capturing those questions live. And we've got some of our engineers on standby observing that channel and trying to answer you in real time. However, if the conversation is a bit more complicated or technical and we can't completely answer them, of course, we'll take the time to supply email addresses and phone number contacts, and we can follow up with you in more detail after the webinar. That's happened to us before when it gets quite deep into the technology and how it works. But for now, please be advised that the Q&A button is there for you and you'll be on mute, and we'll try and summarize the most frequently asked and popular questions at the end of this. In the meantime, as I said, I'd like to introduce Stephen, who's going to take you through the core subject for today, which is about our solutions for centralized busbar protection in digitally enabled substations. And then after about 15 to 20 minutes, he'll have finished the slides and we can capture and repeat any of the popular questions and see where that takes us. We'll do some follow-ups with everyone who managed to listen today, recording the webinar as we go and supplying you with a recording and follow-up notes from it over the next weeks. So we hope you find it very useful. And now I'm going to hand over to Stephen to get going. Thank you.
Okay, thanks very much, Sal, for the introduction. So I think I'll just make a start. So thank you again for everyone for joining this webinar. Hope you'll find it interesting. So the topic of this webinar is centralized protection and monitoring, and I'll go into a little bit of depth about where Synaptec is really contributing to this topic and providing some new and interesting kind of innovations on top of the general movement towards digitalization. So just for a little bit of context to set the scene, so Synaptec is a vendor of sensor systems, and we're based in Glasgow in the UK. So what we've created is a unique passive sensing technology, and that's able to bond multiple sensor types, including VTs and CTs and other types of sensors, onto a single optical fiber. So this means that we can distribute many sensors over a wide area using a single optical fiber, and then deliver that data to a central location wherever it's needed. So this is quite powerful, and it's certainly unique in the industry. It's a very versatile system, and we've already worked with several grid operators and in other application areas such as offshore wind, as you can see on the slide. So just to go into a little bit more depth into that. So what does the solution actually look like? So on this slide, you can see how we've got a single central monitoring unit, which is connected to an optical fiber. And then that fiber is able to visit lots of distributed sensing locations throughout the system, whether that's inside a single substation or far beyond that in terms of overhead lines, cable systems, and even assets that are far offshore. So as I said, we use a unique method to interrogate these sensor points using only light, and we can support voltage, current, strain, vibration, and temperature measurements, all integrated into the same system. Normally, this allows us to deploy 50 point sensors using a single fiber, and that can reach over 100 kilometers of distance, usually. Depending on the quality of the fiber, it may be possible to extend that. And a really crucial point here is that at each sensor location, there's no need for any kind of powered device. It's a completely passive approach, and a lot of the infrastructure that you would normally need to connect sensor infrastructure is just not required here. So it's completely passive. the nature of the measurement is inherently secure and protected against the effects of interference. So it's a nice self-contained system that can see far and wide in the system, and is very flexible about how it's deployed. So that's the general introduction, but I want to highlight some of the challenges that are experienced at the moment in the industry relating to substation protection and monitoring, which is the focus of this presentation. So first of all, substations, particularly as they're migrating towards a digital substation approach, it requires lots of different people to closely coordinate, and those people have different skills, and within a utility, they typically work in different departments. So they all have to be brought together, each with their own highly specialized skills to deliver the full system. And that can involve people from protection, SCADA monitoring system, telecoms and networking, IT, and cybersecurity. All these diverse areas of expertise need to work together to deliver a digital substation. And typically that expertise is kind of siloed within a utility. So that's one of the first challenges, is really the bringing the people together who can actually deliver that system. Second challenge that I wanted to highlight is that utilities already have to manage many assets, particularly the primary assets, but also the secondary devices like the protection relays inside the substation. And in particular, for a digital substation approach, there's also this new type of device, which is the merging unit, and the process bus infrastructure that's needed to make that work and to deliver the measurements reliably. So what this means is there's lots of IDs required in a substation, and each of those requires configuration through the IC 61850 approach, which is relatively complex, and particularly when you're looking at maintaining those devices over time, there's potentially a lot of engineering effort needed to manage that. And the third point I just wanted to highlight today was that typically SCADA systems don't provide a very high resolution of monitoring, and even relatively advanced monitoring schemes using PMUs, they can actually miss some important events, such as if there are fast-acting transients in the system, such as like arcing of a circuit breaker or maybe chattering of relay contacts. These sort of things are for the most part hidden, and utilities don't really have a lot of visibility of the detailed health of their assets. So there's a strong need to move to an approach to maintenance and monitoring of the health of assets, which is data-driven. And in principle, a process bus gives you all that data because it's monitoring the system in a high level of detail. And also it's important to time synchronize everything so that data is actually meaningful and you can compare it over time. If you don't do that, then there's a risk that your engineers and data scientists can't really use the data, or they spend a lot of time trying to patch it up. So we need an approach that's automated and ultimately leads to a kind of safer and easier to manage system. So what I hope to achieve in this presentation is really show you how we can help address some of these key problems. So we've seen a lot of drive in the industry lately towards a centralized approach to protection and monitoring systems in substations. For example, it's a regular feature at the PacWorld events. So essentially what this means is it's consolidating multiple functions which would normally be served by dedicated relays, each with their own CTs and VTs connected, converting that to, rather than multiple devices, consolidating it into a single device which performs multiple functions, going well beyond the multiple functions that typical modern relays already provide. So this will really help make substations much more efficient. They'll be easier to configure, and in the long run, they'll be easier to maintain and safer to operate. These are the sort of general benefits of a digitalized substation architectures. But what I want to show is how Synaptec's approach goes a bit further than that, and it's uniquely suited to a centralized architecture, and goes even further to delivering that kind of efficiency benefits, as well as additional benefits such as like improved footprint in the substation, which is very useful in some cases, and improved carbon footprint as well. So I'll touch on all of these qualities as I go through it. So first, I just want to quickly highlight one of the applications where we've done this already, and we've applied this in the Norwegian, for the Norwegian transmission system operator Statnett, and we've deployed a system in one of their 300 kV substations, which is just northeast of Oslo. So this is a real deployment, and it has some unique features that I just wanted to point out. So first of all, it's a two-in-one system. So we've gone for a centralized busbar protection system, which is the first thing that we've deployed, and we've also rolled into the same integrated system quite an interesting transformer monitoring scheme, where we're doing environmental and mechanical monitoring of an HV transformer in the substation, as well as seeing what's going on in terms of the electrical system. And again, because this is a Synaptec system, I'll just emphasize again that this deployment is centered around a single optical fiber, which visits the CTs and the other sensors out in the yard. So we don't need a power supply going there, it's just an optical fiber. And these are not merging units, these are completely passive units. So effectively with this architecture, we've eliminated the need for a merging unit and all of the redundant telecoms requirements that brings along, and the time synchronization issues that are frequently encountered when trying to configure and deploy these devices. So we've immediately removed a lot of the complexity and removed some powered devices that would need to be installed out in the substation yard. So we're already kind of simplifying the approach. Just to explain a little bit further about the busbar protection scheme. So again, we have a central IED, which we call our interrogator, and that's able to receive synchronized waveform measurements from all of the monitored locations in the scheme. So with this kind of visibility, it's straightforward to do busbar protection, which is what we're performing, and that could be extended to consolidate other functions such as backup protection like breaker fail or overcurrent protection. Could all be integrated into a centralized approach, and it's also very flexible as well. So we can quite readily provide the data to other IEDs as required if the protection functionality was required to be external. So again, I just wanted to highlight that this is very well suited to a centralized approach, where we minimize the number of powered devices in the substation. It's also worth mentioning at this point that redundancy can be delivered in different ways. So for example, we can interrogate the fiber from both ends, so that makes it immune to a break in the fiber. We would still have visibility of the system, or we could have two independent fibers. So either approach would provide the obvious kind of redundancy that's required in this kind of scheme. It's also because we're seeing the entire system sort of simultaneously, we inherently provide time synchronization of all the measurements. So that's quite important for protection, where you need to be very resilient. And although we do normally provide PTP-based time synchronization to provide global time synchronization reference, even if we lose that source, if the clock is offline or some other issue, we still provide relative synchronization of all the measurements. So we're very resilient to other failures, external failures in the system. We can still provide the protection functionality or other functionality that's needed. So before we deployed the scheme for real, we did a lot of testing, and we worked with University of Strathclyde to do that with RTDS. So the point is here that we were able to do all the kind of standard industry tests that are required to prove this type of system, as you know, the industry is obviously very cautious when deploying these types of systems, but we've done all the proving that's required. This is what it looked like inside the lab. You can see our interrogator towards the front there, and the RTDS that supplied all the various signals that are needed. And to sort of cut to the chase here, this is sort of the results from that, and the main thing to point out is that, you know, we passed all the tests, and also that the protection operation was sub-cycle, as you would expect for a busbar protection scheme. So everything was able to be sort of demonstrated successfully. You can see the team from StatNet there joined us for the testing. And once that was complete, we were able to install this in the real substation in Norway. You can see our engineer working with the StatNet engineer to deploy this. And the nice thing is, because it's a passive sensing approach, it's you know, very easy and quick to install. There's no kind of specialized skills that are needed. It's just standard installation procedures. And just to highlight at the bottom right there, you can see our interrogator ID sort of safely installed in the protection cabinet. So so I mentioned some of the kind of the deeper industry challenges that are ongoing, and I want to kind of show how we're working towards addressing these. So something we've been working on is really leveraging all of the potential benefits of our platform. So we provide, you know, high sampling rate of data. All of the data is naturally synchronized, and we would always strive to have that linked to global time reference, so that the data is always useful to be analyzed later. So what this brings is lots of different applications and different timescales. So what I've described today, what I focused on, was the centralized protection approach, where we're a very good fit, but moving up the timescales into sort of multiple seconds or minutes. We're also a very good solution for things like real-time thermal rating and, you know, managing cables and overhead lines, and also system kind of security features like oscillation detection that are, particularly in the UK, becoming a pretty important capability. And then looking kind of longer term, we've basically got an ideal platform here that's able to leverage some of the really detailed monitoring of assets in the substation and provide a really useful new approach to how we do asset management and how we do maintenance in the future. And that's really driven by the fact that we have access to the full waveform data. So we can see what every asset is doing in full detail. And we can also look at that through different sensor types. It's not just the conventional CTs and VTs that we're stuck with. We can do things with temperature, vibration, and strain as well. So we can get a really detailed picture of what assets are doing. So here's a quick screen capture of our software, and it just gives you a feel of, you know, what you can do with this type of platform. You know, you can look at lots of different monitoring locations, potentially over quite a wide area of the system, and you can see in detail what each asset's doing, and we can add sort of customized visualizations to make that, you know, better suited to what exactly the application that's needed. And in particular for a substation, you get a really detailed view of every single asset and what's going on. Here we're just emphasizing this for another one of our installations, where you can probe exactly and see what exactly the waveform is doing. And we also roll in things like power quality information, so you can see the harmonic spectrum being displayed there. And there's also, you know, PMU functionality as well. And as well as the really detailed stuff, which is, you know, occasionally interesting to look at, what's probably more important is what's happening in the system over a long period of time. So here we're seeing some data we've collected from one of our systems over several months, and we're able to correlate different monitored parameters and really understand what's going on in that system. Here we're looking at it visually, but of course you can do this through a kind of a more software-based approach as well to sort of automate the understanding of the system. I just want to briefly touch on another quality that we provide, because we provide the waveform data, or what's sometimes called the continuous point and wave data. And here I just want to clarify exactly what that means. So on the top, we've got a typical output from a synchrophaser, which I've simulated in this case. So this is a P-class PMU. It's providing positive sequence magnitude value. And what the PMU reports is a barely perceivable difference in what's going on. But when you have the continuous point and wave data, you see a very significant change in the behavior of the system. That's something that could be a significant problem and may be located far away, where you typically wouldn't have detailed monitoring of the system. So for example, this could be a large wind farm or some other event was switched into the system, or there's some other reconfiguration that was unexpected. You can really reveal what's going on with continuous point and wave data, which you can't do even with synchrophasers. So what does that mean? Well, it means you can see synchronized event records of what's going on. This is at low voltage, but the same principle applies at any voltage level, where if you can correlate what's going on between different parameters, you get a better understanding of the event and the root cause of that event. So in here you can see notching on the voltage as well as the arcing in the current. So here is, that gives you some clues about, the locality of the event. It must be relatively close. So that time synchronization and the ability to see transients is really valuable. We've also seen some of our friends at the University of Strathclyde have been doing some interesting work recently, looking at how to do quite advanced event classification using continuous point and wave data. And what they've been able to do is, by using a relatively small library of previous events combined with some additional context like the weather and the system state, they've been able to provide a classifier that can deal with events that it's never seen before. So it can tell you things like what the root cause of an event was. So it's not just that a fault occurred and that it was maybe a single phase to earth fault. This approach can tell you that it's something much more specific and useful, like an insulator failed, or there's a line that has fallen. That sort of level of detail that really helps the utility get better value out of their monitoring and helps them direct their kind of maintenance efforts to the right location and send the right type of crew to deal with it. Another interesting point here is that as you increase the sampling rate, you increase the accuracy of this approach. So Synaptec's approach always provides at least 4 kilohertz sampling, and you can see that's providing in the high and mid 90s of accuracy, percentage accuracy here. So this is something we're developing further, and we hope to show really useful capabilities in the future here. Sometimes, however, for many applications, you do just need synchrophasers, and we're already set to do that. We provide a leading algorithm that we've spent a lot of time developing and testing over several years to do this. And the algorithm is very resilient to real world kind of disturbances on the grid. So when you've got the worst possible scenario of harmonics and interharmonics, unbalance, if the frequency is changing kind of radically, we still give you a really good answer. So when you need your answer of your PMU results the most, we've tested it for those kind of situations. It's also computationally efficient, which means we can readily deploy it within our device, and we can even perform the computation in the cloud if that's required. What's also interesting is that because Synaptec's platform is already able to aggregate lots of different measurements, so I mentioned 50 measurements per fiber, So that means you can do 16 three-phase locations. So effectively our system provides 16 PMUs integrated into one box. So that means you can probably avoid having a PDC in the substation because we're eliminating that first tier, that first level of complexity that you would normally otherwise have. And yeah, we've tested this against standard requirements, and even in the worst case test, which is what I'm showing here, we're already exceeding what's required. So just to round things off, I mentioned these specific challenges at the start, but I hope I've shown that we've got a solution here that helps with these problems, significantly helps in some cases. So first of all, with that complex multi-domain knowledge that's required to make this happen, what we're offering is a greatly simplified design through passive sensing, and something that's a natural fit for centralized substations, and will really deliver, efficiency gains in the long term. And similar to that, we're consolidating multiple physical IEDs, in particular the merging units, which are normally needed, into a much smaller number of devices. So that means it's easier to maintain that over time and to configure it in the first place. And third, this lack of data-driven maintenance. Well, our answer to that is we're providing a platform that can provide synchronized measurements, first of all. And those measurements are unique. They can contain, monitoring of other types of parameters, environmental and mechanical, as well as electrical. So we can look at assets in a very detailed way, and all integrated into one platform. So just to summarize, our solution, as I mentioned, it's inherently secure. It's because of the fiber-based sensing approach. It's basically a fit and forget system. So there's very little maintenance because there's no active electronics or batteries or anything like that required at the sensor locations. And with the centralized approach, we can pull data, whether it's around a substation, particularly a larger substation, or at a great distance as well. You can pull that all together and deliver it to a central location where it's actually needed to be used. And that package of data is composed of a unique combination of electrical and mechanical sensors, as I mentioned. And it's also worth pointing out that we can help deliver this with a low carbon footprint, as well as a low physical footprint, which can often help with new substations or with retrofits. So I think that covers everything I wanted to say today. So thank you very much for listening, and we'll be happy to take any questions you have now. So thanks very much.
Okay. Thank you, Stephen. Much appreciated. So this is Saul again. I'm just stepping in quickly here because there were some questions coming in live while you were talking there. And there are two in particular that are probably worth just repeating to everyone here. So sorry to throw you in at the deep end here, but the first one was, I think quite a few people understand what a Faraday effect NCIT, or non-conventional instrument transformer, would be, and how optical sensors work in digital substation applications. But could you explain why we're different? Because I think people were struggling to understand, like, what is the form factor of the CTs we're using and how they differ. So how do you need any kind of special CT or infrastructure to instrument each of these bays in the substation? I think that's probably the way to answer.
Yeah, well, the answer is no, there's nothing special required, but the form factor does have some advantages. Maybe what I'll do is I'll show I've got a couple of slides here that maybe sort of reveal the sort of physical aspects of stuff. And seeing as our head of sensor technologies, Neil Gordon, was kind enough to join us today, Neil can certainly give you a better answer than I can on terms of like the differences between this approach and the kind of the other type of optical sensing.
Yes, I can certainly jump in on that one, Stephen, if you would like. So the other type of optical sensing, as I think you've said, would be an NCIT, which typically means a Faraday effect current sensor, for example, in which a very special type of fibre is wrapped around the conductor, and then it looks at the rotation of the polarization of light to get a measurement of the current. That's quite a different type of device to ours for a number of reasons. It requires a local power source. The actual method of the measurement is very different because the measurement is encoded in the polarization of the light, and it can only reach a distance of somewhere between 10 and 20 kilometers typically from the actual merging unit. So the physics used in our device encodes the measurement in wavelength, which is a lot more robust to things like electromagnetic interference, which means we can operate over much longer distances than the NCITs typically can. As Stephen mentioned in his presentation, we can go up to 100 kilometers nominally from a substation with a single fibre. And we can also multiplex a much larger number of measurements on a single fibre. So again, as Stephen said, we can go up to 50 measurements per fibre, whereas for a merging unit with an NCIT, you would typically get something like 3 or 6 currents per merging unit. So it's really about the scalability and the robustness to distance measurement effects that sets us apart. Great,
thanks, Neil. That's definitely a better answer than I could have given. Does that fully answer all the aspects of that question? Because it was a detailed question.
Yes, I'm sorry, it was. Okay, I think it does. And I think the Neil covered part of one of the other questions, which is, okay, so how many bays can you instrument? So of course, the answer I think was already given there, but just to be clear, per fibre, if we can do 50 locations and it's a 3-phase current measurement per bay, then you could do 16 bays per fibre, would be the right way to think about this. And then the question is how many fibres are available and how many bays do you want to cover? It's completely scalable. So there's no specific limitation on how many locations can be synchronously monitored, whether that's current, voltage, or other mechanical parameters. Well, I hope that's clear. And one other thing to add to Neil's answer, based on the slide that you're looking at here, the point of our technology is that we are able to use industry standard CTs and industry standard VTs, or we can combine them and do combined voltage and current measurements. So the equipment is standard. What we're doing is taking the measurement of the electrical field as it passes through the CT you can see here and passively converting that into light, which we can measure from the interrogator. That's why it's passive, because there's no active components, electronics, power supplies, or data networks at this point. So from the outside, this looks like an industry standard CT or a VT, but it's how we connect it back to the interrogator that makes the difference, because we can do so many of them synchronously. And the only thing connecting them is encoded light, which is why it's so secure. So I hope that's clear, because sometimes people think we're doing some kind of special form factor or special merger units at the remote location. We're not. It is completely passive. Now, so sorry for adding that little bit extra. I just wanted to be clear about the fact that these are very standard and familiar devices, and that's why it's good for the temperature range and the repeatability of performance and accuracy at each location we're installing. So one other thing for you, Stephen, if I may, there was another question here about the protection algorithm being deployed by us. So we should probably just explain for people the distinction between how the interrogator would publish sample values onto a process bus in most digital substations, but your example went a bit further than normal, right, by actually running the protection algorithm on board. So could you just distinguish the different levels of software functionality within the within the interrogator unit for people? Because I think that provoked at least one question where people were a bit confused about how we interact with protection relays and traditional schemes.
Yeah, well, as you said, so we can readily provide the data in whatever format is needed. So for a process bus application, 6150 sample values is how we do that. And so any other device can pick that up. And we've tested that with, I think, all of the main vendors in the industry that provide devices which can read sample values. We've tested that in our lab. So that's one way of doing it. But as you say, in this case with StatNet, we did do that extra step where, you know, we did a phaser-based differential busbar protection scheme built in within the same device that we provide. So that's an option for super kind of fast acting approach where you can act on the measurements immediately as they're generated, rather than sending them out via the process bus. But probably the common case would be to share that information with other devices in the substation rather than integrating the protection. But it's a very flexible approach, so both approaches can be done. It's also it's worth pointing out that going beyond the substation, looking at the protection of lines, one of the common issues with that is how those measurements are synchronized and how they're communicated over a long distance. But we provide a kind of elegant approach to that where you don't need the conventional communications network, and you don't need to deal with the issues of, you know, migration to MPLS networks and these kinds of things, because we provide all the data back immediately where you can perform the protection function in a centralized way. So it works within the substation and at a distance as well. So hopefully that covered that one.
Yes. Okay, that's probably the right answer. I'm just, sometimes the questions are difficult to interpret. I'm sorry, I'm throwing you under the bus here. I think the commercial answer rather than the technical answer here, just to explain to everybody, is that the example that Stephen gave you, where we've been deployed for over a year now with StatNet up in a substation near Oslo, right, in Norway, they were challenging us to go further than anyone has gone before with these concepts. They particularly wanted to understand if it was possible to install one of our schemes as a redundant, or if you will, a shadow scheme to complement and back up the traditional instrumentation scheme. And if StatNet wanted to upgrade the protection hardware in their network, they wanted to know if they could do it with less equipment and with shorter scheduled outage times. You know, traditionally, if you're replacing the busbar protection hardware in a substation like this, you might schedule an outage that lasts 8 weeks. And the fact that we could retrofit one of our systems in 2 days and still work even with total or partial outages occurring within the substation because the sensors are passive, that's a huge benefit for the operator to reduce the outage time that's required to upgrade or back up the scheme. So there's also a commercial application here that says if we can put a lot of sensors in a lot of places and simultaneously measure what's happening at all these points and do it safely, because these devices fundamentally are not powered and you're not using live copper wiring in the yard, that's a health and safety bonus, and it accelerates the time that the outage requires to complete the upgrade or refurbishment of the equipment. So normally our application would be, as Stephen said, that we are simply providing a kind of multi-point or multi-zone faulted section identification scheme and publishing sample values to tell the protection scheme with more precision and accuracy how to respond to a fault and where that fault is contained within an electrical section. But you know, StatNet just challenged us to go a step further and also cover the protection algorithms as well, just to prove that it can be done. That's not normally the way that, you know, digital substations would operate. But I hope that explains the distinction between the particular case study there and the general market requirement and the application that we see in the market. Okay, now I believe that's the summary of all of the questions here catered for, and I think we've repeated everything that came up that wasn't very, very specific. One or two housekeeping notes for everybody who's on this webinar that I would just like to cover off at the end here. So again, thanks to Neil and to Stephen for taking us through this particular application study. We do want to emphasize that there are others that we have recently published and shared with our customers. So if you have a look at our website, which is Synaptec, that's synapt.ec, you'll see previous recordings where we've talked about cable fault detection schemes, how we can instrument hybrid circuits and distinguish between overhead and underground faults. We've got some previous webinars talking about the fundamental technology and how our systems work and how the technology to make CTs and VTs passive actually functions. There are some upcoming ones over the next 3 months talking about other applications for multi-branch or multi-ended circuits and offshore wind and renewable generation applications. But the point is, everything's available on the website, and after this recording, we'll be following up with the people who registered and who were able to attend. So thank you for your time. To give you access to a copy of the webinar, we recorded it today so that you can play it back at your own leisure. And then we'll also supply some follow-up literature, like a kind of small PDF, which only takes up 1 or 2 pages, re-explaining and encapsulating what we're doing and what the key benefits are of this technology application in particular. So please keep an eye out for future webinars. We'll be advertising those on LinkedIn online and also in our monthly newsletters. We will also be following up with everybody individually to find out if there are any specific applications or detailed questions that you've got about what we've said today. So thank you very much, everybody, for attending this session. We hope you found it very useful, and you'll be joining us again in the future when we'll be talking next month about some other applications from our experience in transmission and then in renewable generation. So thank you very much, everyone, and have a great afternoon.